So today we're going to be talking about a variety of different circuital laws, and we are going to start with Ohm's law. Okay. So way back in I believe it was the 1860s, this German physicist by the name of George Simon Ohm started conducting a lot of experiments. And the experiments that he conducted looked a little something like this, okay? So he had a network under test, and these were two terminal networks. And what he did is he electrically excited these networks, okay? So this source that I have on my left, I'm not listing it specifically as a voltage source or a current source because it literally doesn't matter. It could be either of those two things, but it was a DC source. And what he did is he measured the voltage drop across the network under test and the current flowing in through the network under test. And he found that these quantities were proportional to each other. And he called that constant of proportionality resistance R, where our resistance R is defined as simply the ratio of the test voltage divided by the test current. And we can effectively just get rid of those subscript tests, which tells us that resistance is simply the ratio of the voltage drop across an element, network, et cetera, divided by the current flowing into that same network or element, et cetera. And you could rearrange this if you were so inclined to the more familiar V is equal to I times R that you guys learned back in your Engineering 120 series. The reason why I'm presenting it to you this way is because I literally had you do that experiment at the end of last class, right? You had a element under test. You varied the voltage with the DC power supply. You measured voltage and current. And when you plotted those guys in Excel, you should have gotten a straight line. So at the very end of the lab assignment, you were asked what the units for the slope of that line should have been. What did you guys get? Wasn't that long ago. It was like 2 days. So what was on the y-axis? Let's start there. That would have been an odd way to do it, but sure. You could have put the voltage on the y-axis if you were so inclined. I'd be willing to bet that most people put the current on the y-axis and the voltage on the x-axis because you had control of what was going on for the x-axis, right? So you still got a straight line there. And what the slope of that line was actually what's known as conductance, where conductance G is the ratio of current to voltage. So that is simply the reciprocal of the resistance. Okay. So we are not going to use conductance a whole heck of a lot in this particular class. It does crop up very often in later electrical engineering courses, but for the intents and purposes of this class, pretty much every time, and I say pretty much 100% of the time that you see a conductance, you can simply take the reciprocal of it and treat it as if it were a resistance, and you won't be messing anything up. So that is what I would encourage you guys to do. There's at least one conductance problem in your in-class assignment for today. I feel like there are one or two conductance related problems in your homework set for today, and then past that, you will not see it again in this class because it's not particularly important. I am bringing it up simply because this is the slope of the line that you guys derived when you did our experiment on Friday. All right, so we have a simple definition for resistance and a simple definition for conductance as to what quantities that they are related to. Let's talk about these guys in a little bit more detail, okay? So let's start by saying that resistance this is a measure of how difficult it is to pass current through a component or network. So the higher the resistance is, the more difficult it is to drive a fixed amount of current through it, okay? On the flip side, conductance is just the opposite. It is a measure of how easy it is So before we get into more relationships and all of that kind of good stuff, I want to talk about applications for resistance, okay? So you guys, through your Engineering 120 series courses, have applied resistors in circuits multiple times. Why were you doing it? Let's start there. What were some of the reasons why resistors were needed? So to limit the amount of current flowing through a sensitive element or something like that. Absolutely right. So you might recall one of the very first circuits that you were ever asked to make here at Tech was something that looked like this. You were using a 5-volt digital output pin from your Arduino, and then you had a resistor in series with an LED, right? And if you didn't put that resistor in, which I'm sure some of you erroneously didn't put it in, what would happen? Your LED would shine really bright for a split second, and then it would never turn on again because it passed so much current through it that it burned out, okay? So we can talk about why it burned out in context of resistance as well. But our first application is, typically speaking, just limiting the amount of current that we can have flow through a particular element is a reason why we would use a resistance, okay? Just for shits and giggles, does anybody remember what value of resistor you typically use for these LED circuits? 220, okay. So 220 ohms. You could use a higher value resistor, but it would cause the LED to shine less brightly, right? And the higher the resistance you put in there, the dimmer it was. And when you got up to around a 10 kilo ohm resistor, effectively the device just wouldn't even turn on anymore, right? You guys may have done that accidentally or on purpose, whatever. All right, so let me put over here just a quick note. So resistors can be used to limit current flow in a circuit, okay? That's probably their most common application, but there is another application that a lot of us, or probably your parents, see. in their everyday lives. And that is that resistors are used, or resistors can be used to convert electrical energy into heat. In fact, that's really what a resistor is doing when it is limiting the current of a device. It's taking up excess energy and converting it to heat so that that energy isn't applied to the sensitive equipment. So a place where a lot of us are probably seeing this application right now is in our space heaters, right? We have a space heater or something like that in our dorm room, our office, or whatever. It contains a really thin strip of wire, usually nichrome wire. Nichrome is a particular material that's meant to be able to carry a lot of current without melting. So it gets really, really hot. You'll see it start glowing red, and then we use a fan to just blow the heat off of that glowing red hot wire into our room. That's all a space heater is a resistance designed to get really hot, and then we blow that heat away. How many of you or your parents own an electric stovetop? Exact same thing. So we can actually infer something from this, okay? Resistor converts electrical energy into heat. Can a resistor store energy? No. All it can do is take electrical energy and convert it into heat. It has no energy storage mechanism or anything like that. So that means that resistors will always be absorbing power or absorbing energy. They can never supply positive power or energy. And so that brings us to something interesting with Ohm's law, okay? So I'm going to introduce the circuit symbol for a resistor, which you guys should all be familiar with. So here's our schematic symbol for a resistor, right? Let's say that the voltage drop across the resistor, V sub R, has this particular polarity, and the current flowing through the resistor, I sub R, has this particular direction. In this case, Ohm's law can be written as the voltage drop across the resistor, V sub R, is equal to the current flowing through the resistor, I sub R, times R. So V is equal to IR, just like we're all used to, okay? If instead we have a resistance and the voltage drop has the opposite polarity, but the current is flowing through the negative polarity terminal, in order to force this resistor to be absorbing power, we're going to have to add a negative sign to our equation. This is exactly what the passive sign convention tells us, okay? So in this particular case, the voltage drop across the resistor will be negative IR times R. So effectively, when the current is flowing into the positive polarity terminal for a resistor, or of a resistor, Ohm's law gets a positive sign. When the current is flowing into the negative polarity terminal of a resistor, Ohm's law gets the negative sign. That particularly simple. All right, so let's talk about resistance here a little bit more, okay? So what's the resistance of a wire? Do you guys used wires in building your circuits and stuff like that? Did you ever take into account the resistance of the wire? No. So I would say that based on your prior experience, you have made an assumption, whether it was intentional or not, that the resistance of a wire is 0. That is a reasonable assumption to make in specific conditions, And now I want to explain to you why that is a reasonable assumption to make, okay? So resistance R, and I believe that you guys have been shown this equation before in Engineering 121. I don't know for sure because the Engineering 121 class has changed significantly since the last time I taught it, but way back in the day when I taught it, this was covered. So resistance is equal to rho E times L over A. Is this vaguely familiar to any of you guys, or is this new? Physics 202? Okay. So in this equation, rho E is the electrical resistivity, typically having units of ohm meters or more likely ohm centimeters. L is length. We'll just say arbitrarily it's measured in meters. And A is cross-sectional area measured in meters squared. So what I want us to do is to calculate the resistance of a piece of wire, like the ones that we've used in our previous classes, okay? So in our previous classes, we had AWG, so that's American wire gauge number 22, copper wire. What's the longest section of wire you guys think you might have used at any point in your Engineering 120 series classes? 5 inches or so? Okay. So let's use something a little bit longer. Let's say we have like a meter. Okay. So that would be a little bit over a yard or a little bit over, 36 inches. So significantly longer than any of the wires that you guys have used. Okay. So let's say that we have a length of 1 meter. The diameter of AWG number 22 wire, don't remember it off the top of my head. I feel like it's a little bit less than a millimeter. Mm-hmm. 0.644 millimeters or 0.644 times 10 to the minus 3 meters. And if we had copper wire, the resistivity of copper, we'll look that up real quick, is 1.68 times 10 to the minus 8 ohm meters. Okay. So if we put these 3 parameters into our expression for resistance, we would find that the resistance of a meter-long section of wire, again, much longer than what we would typically expect to use in the simple circuits that we build, would be 1.68 times 10 to the minus 8 ohm meters times our length of 1 meter. For our cross-sectional area, that's going to be pi over 4 times our diameter squared. So that's 0.644 times 10 to the minus 3 meters quantity squared. And let's throw this in our calculators and see what we get. So 1.68 times 10 to the minus 8 divided by 0.25 times pi times 0.644 times 10 to the minus 3 quantity squared. I got 0.0419 repeating, so let's call that 42 ohms, or 1.997 milliohms. So a 1 meter long section of the wire that we've used in our previous classes, and we're going to be using 22 gauge wire for anything we do in this class as well, has a resistance of 41 or close to 42 milliohms. How does that compare to the smallest resistor that you guys used in your previous classes? Well, it's right up here, right? So how does 42 milliohms compare to 220 ohms? It's thousands of times smaller, okay? So this is the reason why we can neglect wire resistance in our circuits most of the time, okay? Now, for those of you that go out into industry and you're having to wire up things like HVAC units to a load center that might be hundreds of meters away and things like that, the resistance of the wire can start to make a difference. Because since it's a real wire, it does have some resistance. It will have some real amount of current flowing through it. And so the voltage drop across that wire can be large enough to cause your equipment to operate incorrectly. So out in practice, as electrical engineers, interns, and stuff like that, wire resistance might matter. In this class, it definitely will not. Okay, so I just want to make you aware of that. All right. Last couple of things I want to talk about in terms of resistance. Notice here that the unit of resistance was ohms, just a volt per amp, right? So we can go ahead and just put that up here. So 1 ohm is equal to 1 volt per amp. For conductance, we have what's known as the Siemens, symbol is capital S, where this is an amp per volt, or the inverse of an ohm. So power, excuse me, that should totally be a P, absorbed by a resistor is going to be the current flowing through the resistor times the voltage drop across the resistor. Always, always, always. This could also be written by substituting in Ohm's law as the voltage drop across the resistor squared divided by the resistor value, or the current flowing through the resistor squared times the resistor value. So these are power relationships where we either know both current and voltage, or just voltage and the resistor value, or just current and the resistor value. So depending on what information we're provided, we can choose whichever equation gives us the answer we're looking for. And then for conductances, we obviously have the current through a conductance times the voltage drop across a conductance, which would be the same as the voltage drop across the conductance squared times G, or the current flowing through the conductance squared divided by G. All right, so we've spent 25 minutes talking about resistance, which I feel like most of you guys before you came in here thought you had a pretty good grasp on. Hopefully you feel, I don't know, even more confident now. Any questions about this stuff before we move on to different things? Yes, sir.
Could you go back up to what you wrote for the conductance for the
I over V. So over to the right-hand side, we have the units of conductance as 1 Siemens, which is the same thing as an amp per volt, or the inverse of an ohm. Yep, capital S for Siemens. Named after the German scientist that the company Siemens Electronics is named after. Same dude. Any other questions about resistance and conductance? All righty. So now let's talk about, let's do Kirchhoff's voltage law first. All right. So in mathematical form, Kirchhoff's voltage law is as follows. Effectively, the closed line integral of the electric field vector dotted into a differential line element vector is equal to 0. So this should look similar to you guys. It looks pretty damn close to our equation for voltage that we talked about at the beginning of our last class meeting, except that we have a closed line integral in this case, instead of a line integral just between two specific points in a circuit, okay? So what this really tells us is that the sum of the voltages around any path in a circuit, actually, let me write this, any closed path must equal to 0. So let's talk about why this is. So voltage, we learned on Friday's class meeting, is the amount of work required to move charge from one point in a circuit to another point. So anytime that we see a voltage, work is being done. So we have a transfer of energy, okay? So what Kirchhoff's voltage law tells us is that the total amount of energy transferred moving charge around has to be equal to 0. That is just the law of conservation of energy. Because if we created or destroyed energy, meaning that the total sum wasn't equal to 0, we have violated our laws of physics. So KVL, as it's commonly known, is just the law of conservation of energy as applied to circuits. So it is very similar to Telegen's theorem, which is saying some of the powers added together must equal to 0, because it's effectively explaining the same exact phenomenon, just from a slightly different perspective. All right, so let's look at some circuits, and I use that term very loosely, to see what KVL can do for us, okay? So let's say that I have a 9-volt source like so. Connected to some resistance R. Don't know what that is just yet. And then we have a 5-volt source over here. And we are interested in figuring out what the voltage drop across that resistance is with this particular polarity. So KVL tells us that the sum of the voltages around this closed path in a circuit must be equal to 0. So effectively, if we have a bunch of known voltages and then only one unknown voltage, we can simply write an equation following some particular direction, it doesn't matter, adding up all of those voltages together, setting it all equal to 0, and then we should be able to find the unknown quantity, okay? So generally speaking, how I like to write my KVL equations is I tend to start in the bottom left-hand corner, and then I follow a clockwise path around my circuit, okay? So I might start right here, go up across the 9-volt source, to the right across my resistor, down across my 5-volt source, and then to the left across that short circuit. Actually, I forgot to talk about something related to resistances, so let's do that real quick, like, sorry for forgetting something. So short circuits and open circuits. My apologies for forgetting to do this. So if I wanted to represent a short circuit in a circuit, that would literally just be a section of wire. Okay. Now we know for this class that a section of wire has a resistance of 0 ohms. So what does that mean about the voltage drop across a short circuit? It'll be 0 because of Ohm's law, right? V is equal to I times R. So for any amount of current flowing through a 0 ohm resistance path, the voltage drop will always be 0 volts. So anytime we see a short circuit, we know, and by a short circuit, I mean, a section of wire or anything like that, we know that the voltage drop across that is always 0. An open circuit will be represented by the lack of a connection between 2 points in a circuit, okay? The resistance of this is infinitely large, okay? So for any given voltage, what's the value of current flowing through a short circuit? So we would have some voltage divided by infinity is going to look like 0 amps. So short circuits have no voltage drop, open circuits have no current flow. And it's because of the resistance that they represent. All right. Saying that now, we know what to do with the bottommost leg of this thing. Okay. All right. So if I were to write a KVL equation for this thing, how would I go about doing that? Well, what I'm going to do is I'm going to put a negative sign anytime I see the negative polarity terminal of a voltage first. And I'm going to put a positive sign anytime I see the positive polarity terminal first. So if I'm going up through the 9-volt source, do I see the negative polarity terminal first or the positive polarity? Negative. So I would have, so let's just put KVL here, negative 9 volts. What would I have next? Negative VR. And then lastly, plus 5 volts is equal to 0. Solving for VR, that would look like negative 9 volts minus 5 volts is negative 4 volts. Now, just for the hell of it, let's start here in the top right-hand corner and go in the opposite direction and see what happens. Okay. So I'd be going across the resistor, down through the 9-volt source, across that section of wire, up through the 5-volt source. So for this path, our KVL equation would look like VR, because we see the positive polarity terminal first, plus 9 volts, because once again, we see the positive polarity terminal first, minus 5 volts, because we see the negative polarity terminal first, set that equal to 0, rearrange, VR would be equal to negative 9 volts plus 5 volts is once again negative 4 volts. So it literally does not matter at all where we choose to start writing our KVL equation or what direction we choose to follow around our closed path. We are going to get the exact same result every single time. So just because I like to start at the bottom left-hand corner and go clockwise doesn't mean that you have to. Okay, you can do whatever the hell you want as long as you start and end at the same point in your circuit, and you put plus signs anytime you see positive polarity terminal first and minus signs whenever you see the negative polarity terminal first. You're going to get the same answer as me 100% of the time. Now, unfortunately, it's going to be few and far instances in between where this is all we have to do, right? So we can use Kirchhoff's voltage law in combination with Ohm's law to find out much more things about any given circuit, okay? So let's say that I have this guy right here. "12-volt source, an 8-ohm resistor, a 10-ohm resistor, a 4-volt source, and I am interested in finding the voltage between these two terminals." Actually, let me erase something. Let me make this harder. Let's put a dependent source in here. And let's make this 1.6 Vx. So the voltage that is supplied by that source on the right is dependent on the voltage seen between those two terminals in the middle of our circuit. So this is probably much more difficult than anything that you guys saw in your engineering 120 classes, just because of the presence of that dependent source, right? Everything else is pretty straightforward. That dependent source makes things a bit gross. Okay. So we have two unknown voltages in this circuit. Or let me rephrase that. We have two completely undefined voltages in this circuit, okay? We have a voltage drop across our 8-ohm resistor, and we have a voltage drop across our 10-ohm resistor, because we don't know enough about the circuit to assume that those things could be zero, okay? So I want somebody to assume a polarity for the 8-ohm resistor. Positive polarity on the left or positive polarity on the right. Just somebody hit me with something. Positive polarity on the left. All right. So let's call this voltage V8. And just to be a jackass, I'm going to choose the polarity of the voltage across the 10-ohm resistor to be opposite. Okay. All right. So let's figure out what we're actually looking for in this circuit. Okay, that might be useful for us to have a goal. Okay, so I'm going to say that what we are looking for in this particular circuit is the power supplied by our dependent source. So if we want the power supplied by a source, what two pieces of information are we going to need to know? Let's start there. The voltage drop across the source and the current flowing through the source. Okay. So I want you guys to choose a direction for the current flowing through the source. Up or down? Up. Okay. So this will be the current I dependent. And based on things here, we know that the voltage drop across the source is 1.6 Vx. The current flowing through the source, whenever we figure that out, will be I dependent. And because the current is flowing into the negative polarity terminal, just multiplying those two quantities together is going to give me my supplied power based on passive sign convention. Okay. So we've now broken this problem into two smallerish steps. We need to figure out what Vx is, and we need to figure out what I dependent is. Okay. So how might we go about doing that? Well, the only things that we've covered to this point are Kirchhoff's voltage law and Ohm's law. So I feel like it's going to involve those two things. So let's start by writing a KVL equation around the outside. Okay, so this is just something I made up, so it might take more steps than I'm expecting. It might take fewer. As per usual, I'm going to start at the bottom left-hand corner and I'm going to go clockwise around this loop. Okay, so my KVL equation might look something like this. Negative 12 volts plus V8 minus V10 plus 1.6 Vx is equal to 0. So before we move on from this, does anybody have a problem with this equation? How I've written my KVL expression? I believe I've followed all of the rules that I have established. Everywhere I saw a negative polarity terminal first, I put a minus sign. Everywhere I saw a positive polarity terminal first, I put a plus sign. I started from the bottom left-hand corner. I went clockwise around that path, around the perimeter of the circuit, and I started and ended at the same node. Okay, so I feel like that's pretty okay. So we have one equation and 3 unknowns. So we can get rid of a couple of those unknowns by using Ohm's law here, okay? So let's come down. And let's write some Ohm's law expressions. Okay. So Ohm's law is useful whenever I have resistances, right? So we know that V is equal to I times R. So I could say that V8 is equal to I dependent times 8 ohms. So let me start. Is this correct? So I think you're shaking your head no. Why are you shaking your head no? It should be negative. Why should it be negative, Wall? Exactly right. So our current I dependent, which is flowing around that outside loop, is going to be entering the negative polarity terminal of the 8 ohm resistor. So we should have a minus sign right here, right? Whenever current flows into the negative polarity terminal, Ohm's law needs a negative sign. So I want you guys to tell me what our expression for V10 should be. I dependent times 10 ohms. Any need for a negative sign? No, because the current's flowing into the positive polarity terminal. So if we substitute those two quantities in to our KVL expression, so let's just do that right here, we would have negative 12 volts minus I dependent times 8 ohms plus I dependent times 10 ohms plus 1.6 Vx is equal to 0. And we can clean this up a little bit more just by lumping those I dependent terms together. I'm going to move the constant term to the other side of the equal sign as well, okay? So I think we would have I dependent, and I'm going to have positive 10 minus 8, so that's just going to leave me with 2 ohms. I'm just going to write a note up here. That's 10 ohms minus 8 ohms plus 1.6 Vx is equal to 12 volts. My algebra okay? I am notoriously shitty at algebra, so there's a distinct possibility it isn't. You are correct. Because there was a minus sign here, minus a positive quantity. Thank you for that. So instead of this being 10 minus 8, it should be 10 plus 8. Told you guys I was shitty at algebra. Thank you for the catch. 18 there. All right. Now does this look correct? Okay, so we've got things down. So we had effectively one equation, three unknowns. Now we used Ohm's law to substitute a couple of things in. And so we've got one equation with two unknowns, I dependent and Vx. So we're going to need to come up with another relationship. Well, Kirchhoff's voltage law tells us that the sum of the voltage drops around any closed path, meaning if we start and end at the same node, have to be equal to zero. So to me, there are two other closed paths that I could take here, okay? So I could write a KVL equation around this path because I'm starting and ending at the same node, or I could write a KVL equation around this path. And they don't necessarily have to be in a clockwise direction like I've indicated. That's just what I'm used to doing, okay? So do we want to do the light blue path or the green path? Because we've already done the outside and that's the only other path we could have done. The blue, okay? So KVL around the blue path. So that's going to be negative 12 volts plus V8, where we know that V8 is negative I dependent times 8 ohms. So I'm just going to substitute that in there directly. Plus Vx is equal to 0. And rearranging this guy a smidge, we're going to have negative, son of a bitch, hold on. I just noticed another mistake up here. That should have a negative sign out in front. So negative I dependent times 8 ohms plus Vx is equal to 12 volts. All right, so because I've managed to screw this, what should be easy for me problem up at least twice already, I'm going to double check these things. So negative, negative, I'm keeping all that stuff on the left-hand side, so that's why that gets a negative sign. 8 plus 10 together is 18, so that seems legit. Plus 1.6 volts, or excuse me, was plus 1.6 Vx seems legit. Move the 12 over, so that's why it's positive there. In my second equation, I'm keeping the negative I dep times 8 ohms on the left-hand side, so that's fine. I'm keeping the Vx on the left-hand side, so that's fine. I'm moving the 12 over, so there we go. So now I have two equations and two unknowns. So it seems like I should be able to solve this system. We could do it by hand, except that I'm never going to bother doing that because that's what we have calculators for. So let's use the system solver capabilities of our calculators to find these things out. Okay? So to me, this looks like a two equation, two unknown system. So on my Casio 115, I'm going to option 5 for systems of equations. And then, excuse me, I press mode and then 5 to bring up my system solver. And then it's option 1 for a two equation, two unknown system. So the coefficient for I dependent in my first equation is negative 18. The coefficient for Vx in my first equation is 1.6. My constant term is 12. In my second equation, my coefficient for I dependent is negative 8. My coefficient for Vx is 1, and my constant term is, once again, positive 12. Solving that system of equations, what I wind up getting is I dependent is equal to 18/13 of an amp, and Vx is equal to 300/13 of a volt. Did anybody else get those same results using their system solver? Okay. So, assuming I don't have any further mistakes buried in this problem, we now actually have all of the information that we need to solve for that power that we were originally looking for, right? So if we come up here to the top, that's going to be 1.6. What are the units on that 1.6? Unitless or volts per volt. Sure. So I can just leave it as 1.6 or I can write it as 1.6 volts per volt. The X was 300 over 13. I dependent was 18 over 13 amps. And so I wound up getting 8,640 over 169 watts, or for sane people that like decimals, 51.124 watts. So before we move on from this problem, does anybody have any questions? Because we buried a lot of things in that one question, right? We did KVL. We used a couple of times. We performed Ohm's law a couple of times and also had to make sure that we were consistent with the sign convention for Ohm's law. We applied the passive sign convention. We also had to use our calculators to solve a system of equations. So a lot of the stuff that we're going to be doing in this class, we buried in this one simple problem. Okay. So anybody got any questions, comments, or concerns? All right. So I'm surprised none of you guys have mentioned this. Usually I tend to have students complain about, well, why the hell do you get to define a voltage Vx across that gap in the middle of the circuit? There's nothing there. Who cares? And I mean that specifically because how did we define voltage on Friday? Potential difference between 2 points. Are those two different points? So why the hell can't there be a voltage across those 2 points? That's literally all the voltage is, okay? So having voltage drops across open circuits is 100% fair game. Think about it as if we had literally just applied a multimeter across those 2 points and we're measuring what the multimeter is going to tell us. That is simply going to be whatever the sum of the voltage drop across the 10 ohm resistor is and the 1.6 dependent source is. Get the signs right on your KVL loop. Or it's the same as the sum of the 12 volt source and the 8 ohm resistor. Again, making sure your signs are right according to KVL. Okay, so since you guys are not asking questions, let's move along to Kirchhoff's current law. Okay. So I can't remember off the top of my head what the fancy mathematical definition for Kirchhoff's current law is. So instead, I'm going to draw a picture. Okay. So let's say that we have some node point here. And we have several wires as part of a larger circuit connected to this node. And I'm going to define a current I1 flowing in. Let's define I2 flowing out of the node. I3 will flow out. I4 will flow in. And I5 will flow out like so. So there are three different ways that we can express Kirchhoff's current law, and they're all essentially the same thing. So we're going to start with the one that you guys are probably most familiar with. So when you learned Kirchhoff's current law in the Engineering 120 class, how did you learn it? Anybody remember? So the sum of the currents flowing into a node must equal the sum of the currents flowing out of a node. Absolutely. That's the first way that I learned it as well. So if I put the currents flowing in on the left-hand side of an equal sign and the currents flowing out on the right-hand side, and I'm just going to make a note here. These guys will be in, these guys will be out. So I1 is flowing in, I2 is flowing out, I3 is flowing out, I4 is flowing in, I5 is flowing out. So that's what my KCL expression would look like. Anybody have any problem with that? Okay. So there's nothing particularly wrong with this approach, and I do tend to use it occasionally, but I am much more likely to wind up using one of the next two formulations of KCL. Particularly what I'm going to call KCL number 3 once we get to doing what's called nodal analysis. So our second formulation for Kirchhoff's current law is simply going to be the sum of the currents entering a node must equal to 0. Now, this does not mean I1 plus I4 is equal to 0, okay? So let me explain what I do mean by it, all right? So I1 is flowing in, so it's going to get a positive sign. Since I2 is flowing out, negative I2 is flowing in, so we would have minus I2. I3 is flowing out, so we would have minus I3. I4 is flowing in, so we would have plus I4. And I5 is flowing out, so we would have minus I5. And we set this equal to 0. So effectively, this is the exact same expression that we got from KCL number 1 if we moved all of the out terms to the left-hand side of the equal sign, okay? So it means the same thing, it's just looking at it from a slightly different perspective. And KCL number 3 is effectively the exact same thing as KCL number 2, except that we'll say that all of the currents exiting a node have to come together and make 0. So that would be negative I1, because negative I1 is exiting, plus I2, because I2 is exiting, plus I3, because I3 is exiting, minus I4 plus I5 is equal to 0. And this is the exact same thing as the expression above, except everything is multiplied by a factor of -1 because we chose the opposite direction as our reference, okay? So once again, all of these three different ways of looking at Kirchhoff's current law give us the exact same results. So I tend to just use whichever one makes the most sense to me at any given moment of time, depending on what it is that I'm looking for, okay? All right, so let's talk about applying this thing. Once again, we'll start with something fairly simplistic, and then we'll move along to something a little bit more difficult, okay? So if I had a 5 amp source direction up, connected in parallel with, let's call this a 6 ohm resistor, and then a 2 amp source direction down. And let's say that I am interested in finding the current flowing through the 6 ohm resistor direction up. We could use Kirchhoff's current law to directly solve for this, okay? So we are going to apply Kirchhoff's current law at a node. This particular circuit has exactly 2 nodes, one on the top or one on the bottom. So I want one of you all to make an arbitrary decision and tell me if we're applying KCL at the top node or the bottom node. Bottom node, okay. So KCL something at bottom node. And I'm just making a note of this so that we can make sure that we're obeying the rules correctly. Somebody else tell me if we want to look at KCL formulation 1, 2, or 3. 1. All right. So KCL number 1 at the bottom node. So that means that currents that are flowing into the bottom node have to be equal to the currents that are flowing out of the bottom node, okay? So which currents are flowing into the bottom node? 2 amps. And that's the only one that's flowing in. So that means by default that the 5 amps and I6 are flowing out. So we could rearrange this and we would see that I6 is equal to 2 amps minus 5 amps is a -3 amps. Just for shits and giggles, let's do a different formulation of KCL at the top node and make sure that it gives us the same result. So 2 or 3? 2. All right. So KCL number 2 at the top node, okay? So KCL number 2 tells us that currents that are entering the top node should get a positive sign, and currents that are exiting the top node should get a minus sign. So which currents are entering the top node? 5 amps and I6. I2 is exiting the top node, so it's going to look like -2 amps. We set this equal to 0. Rearranging, we would have I6 is equal to -5 amps plus 2 amps is once again -3 amps. So regardless of which version of KCL we choose to use and which node we choose to apply it to, and let me put a big asterisk there, for one of these 2 node circuits, we are going to get the exact same result. So any question about this before we start incorporating Ohm's law as well? All right. So now let's say that I have six amp source, a 5 ohm resistor, 10 ohm resistor. And a 3 amp source like so. And I want to find the power absorbed by the 5 ohm resistor. So if I'm trying to find the power absorbed by a 5 ohm resistor, what pieces of information might I need to use or need to find in order to do that? Let's start there. So we could either find the voltage drop across the resistor, which would allow us to to find the power using the relationship V squared over R. Or we could find the current flowing through the resistor, which would allow us to use the equation I squared times R. Okay, so voltage or current, either one will work. So I'm going to define both of those things. Okay, so just for the sake of argument, I'll let you guys choose. Should the voltage drop across the 5 ohm resistor have positive polarity on top or negative polarity on bottom? Positive on top. Okay. And do we want our current flowing through our 5 ohm resistor to be flowing up or down? Down. Okay. Now we've also got that 10 ohm resistor over there, and we can't ignore it. So I'm going to go ahead and I'm going to choose to assume a polarity for that particular voltage. And I'm going to choose it to be on top. And I'm going to choose a direction for the current. And once again, just to be a dick, I'm going to put the direction opposite, like so. All right, so the purpose of this exercise is for us to apply Kirchhoff's current law and Ohm's law, but I'm going to do something else just really quick here. I'm going to apply Kirchhoff's voltage law so that we can actually make an observation about these things, okay? So if I were to apply Kirchhoff's voltage law around this particular path, what would I get? Negative V5 is equal to 0, or V5 is equal to V10. So the reason why I'm making a note of that in particular is two things. A, now we can completely get rid of a variable V10 from the jump and just call it V5, but we can make a broader observation from that, okay? How are the 5 ohm resistor and the 10 ohm resistor connected to each other? They're in parallel, okay? So what we've just used Kirchhoff's voltage law to prove is that anytime we have any elements connected in parallel, they have to have the exact same voltage drop across them because Kirchhoff's voltage law forces that to happen. So any parallel combination of elements, doesn't matter if it's voltage sources, current sources, whatever, resistors, capacitors, inductors, if they're in parallel, the voltage drop across them has to be the same thing, okay? So I'm going to go ahead and just get rid of that V10. And I'm just going to use that one voltage V5 ohms for everything because I can. It's common to all of those elements because they're all connected in parallel. Okay, so with that out of the way, we haven't yet used KCL number 3. So that's the one that I'm going to force us to do. So that means all of the currents that are exiting a particular node are going to be positive. So do we want to apply this at the top node or the bottom node? Top node. All right. So currents that are exiting the top node are positive. So the 6 amp is entering the top node, so that's going to give us -6 amps. I5 is exiting the top node, so that's going to give us plus I5 ohms. I10 is entering, so that's going to look like minus I10 ohms. 3 amps is entering, so that's going to look like minus 3 amps is equal to 0. And so we now have one equation with two unknowns. So what we're going to use is Ohm's law to express both of those resistor currents in terms of that common voltage V5 ohms that's across everything, right? So let me just sneak down here and write Ohm's law. Okay. So using Ohm's law, what would I5 ohms be in terms of V5 ohms? V5 ohms over 5 ohms. Absolutely right. So if V is equal to I times R, I is equal to V over R. Perfectly reasonable. Let's just double check some things here really quickly. Is the current I5 ohms flowing into the positive polarity terminal? I would agree it is. If it's flowing out of the negative, it's the same as flowing into the positive. Meaning, let me that I5 ohms on the top, is that the same current? Yes. Is it flowing into the positive? Absolutely. So into the positive polarity terminal is the same thing as out of the negative polarity terminal, okay? So our Ohm's law expression down here should get a positive sign, so we don't need to make any modifications. What about our expression for I10 ohms? Negative V5 ohms over 10 ohms, because the current is flowing into the negative polarity terminal and out the positive polarity terminal, right? So just to be clear here, if this is the negative polarity terminal and this is the positive polarity terminal of V5 ohms, the current's flowing into the negative or out the positive. So we get negative V5 ohms over 10 ohms, and we can just substitute those things in, right? So I'm just going to come back up here. I'm going to move the 6 amps and the 3 amps over, so that's going to give me 9 amps over here. I5 is V5 over 5 ohms minus I10. So I'm going to have minus negative, so that's plus V5 over 10 ohms is equal to 9 amps. And then I can solve this for V5 ohms. So let me do that really quickly. So if I did this correctly, and I believe that I did, I got 30 volts. Using this piece of information, then, the power absorbed by our 5 ohm resistor would be 30 volts squared divided by, that's a shitty looking 5. $180 watts. All right, I've got about 3-ish minutes left of things that I want to talk to you guys about. So before I do that, does anybody have any questions regarding this particular problem or anything? Okay, so the first question that I want to ask you guys is pertaining to this particular circuit, okay? So if I had swapped the order of the 5 ohm resistor and the 10 ohm resistor, meaning that the 5 was now on the right and the 10 was now on the left, would that make any appreciable change to the circuit whatsoever? So what I mean by that specifically, would the current flowing through either of the resistors change? No. Would the voltage drop across either of the resistors change? No. Would the power absorbed by either of the resistors change? No. So changing the order of those two elements wouldn't matter. That's actually true for any elements that are connected in parallel. The order that they are connected in parallel in does not make any damn difference whatsoever. So we can move stuff around if it helps us to either visualize things or simplify things and stuff like that, okay? So for parallel elements, order literally does not matter. Now let's look at something else just real quick having to do with series connected elements, okay? So let's say,
Sorry, I don't understand.
shut up, phone. Don't even know why the hell Siri was spying on me. So let's just say that I have something pretty simple. 10 volt. Like so. I am going to assign the voltage drop across the 8 ohm resistor like so, and the voltage drop across the 5 ohm resistor like so, just for the sake of argument. So if we were to apply Kirchhoff's current law at this node, I could say that the current that is leaving the 10 volt source must be equal to the current that's flowing through the 8 ohm resistor, right? Because the current flowing in, which is I 10 volts, has to be equal to the current flowing out, which is I 8 ohms. Everybody okay with that? If I were to apply KCL at this node, I could say that the current flowing in is I 8 ohms, and that must be equal to the current flowing out, which is I 5 ohms, right? And similarly, if I were to apply KCL at this node over here, I 5 ohms is flowing in, I 4 volts is flowing out, and so we can say that all of those currents are equal to each other. So effectively, what I am trying to impress upon you guys right here is that whenever we have elements connected in series like this, they all have to share the exact same amount of current because there's no place for the current to branch off or change, right? So at every single node, I in equals I out. So we can modify our definition for what it constitutes to be in series as instead of two elements connected to each other where they don't have any branching paths. Now it's just all currents that are connected together without branching paths that carry the same current. So all 4 of these elements are considered to be connected in series. Okay, that's it. Oh, well, I guess actually one last thing. Would it make a damn bit of difference if I change the order of those elements? Not at all. So the order of elements in parallel doesn't matter, and the order of elements in series also doesn't matter. Now I'm done ranting. All right, in-class assignment time.